Okay, so let's start. Good afternoon, everybody. So I wanted to talk about a work that we are performing at NIMESIS on the 4D printing, so the additive manufacturing of shape memory alloy. Okay. So just first of all, additive manufacturing is not our core business. Our core business is to manufacture and to offer a component for space application. So mainly release device, deployment mechanism, dismantlement. We also have another unit dedicated to mechanisms, so not only component, but integrated component. We also propose engineering, so simulation, characterization, and so on. And last but not least, materials, where we study different kind of shape memory alloy, high temperature shape memory alloy, very high temperature shape memory alloy, and also the process, and more precisely, the 3D and 4D printing. So the project overview, so we perform this work on GSTP, ESA GSTP project. It was a 2 years project that we just finished in January this year. This project was done with Thales Alenia Space as a end user and final user, and with the LEMS 3, which is a laboratory which study materials, mechanical and microstructure, and they do have 3D metallic 3D printing machine. And the objective was to assess the use of additive manufacturing for shape memory alloy, meaning do we have the same property, the strain, the shape recovery from after the process of additive manufacturing. And of course, finding some application and mechanism that are suitable for 3D printing. So let's go more into technical details. So to understand what is the 4D printing, we need to first understand what are the shape memory alloy. So shape memory alloy are a family of alloy that can change shape at a given temperature. So actually there are two solid states, and it's going from one solid state to the other one that gives this change of shape. So going from martensite to austenite, it's a change of crystalline structure on the material, and it will change the shape of the material. So by changing shape, it will create strain and stress. And with the strain and the stress, we can create actuators. So making movement, displacement, and also stress. Yes, and one thing is that this temperature, the transition temperature, will depend on the stress, on the temperature and on the stress, and it's all linked to the chemical composition of the alloy. Okay. Can you put the video? Or so a small video to just give you an idea of. So it's a small demonstrator. So the small spring that you can see, it's very tiny spring, shape memory alloy spring, that can push a weight of, here it's 2 kilo. So by heating, the spring will elongate and push the load. On the drawing, just on the image just above, you can see another way of working where the spring will retract by heating. So actually, all the solicitation mode can be imagined. So traction, compression, torsion. So it gives really a very wide playground to imagine new mechanism. So the transformation temperature depends on the chemical composition, and we know that additive manufacturing shows quite complex thermal process. So the main question, the first question was do we have the same functional property with this with additive manufacturing? Okay, so the technology that we use is the selective laser melting. So a first layer of powder is sprayed on the plate. Then the laser will melt some part of the powder. Then a second layer will be displayed, and successively the laser will melt the powder until the desired component is shaped. So it's a very traditional additive manufacturing process that is already used in space in many other fields. And the other way around, okay. So and what is the 4D? Because normally we are using the term of 3D. So the fourth D, the fourth dimension, is given by smart material, and shape memory alloy are part of the smart material. So the idea is really to couple the advantage of additive manufacturing and the property, very interesting property of shape memory alloy. So as you can see on this video, it's a small demonstrator to see some complex kinetic that we can imagine with additive manufacturing. Okay. So the work performed. So we start with the powder, which is one of the most difficult parts. The first question was, shall we use pre-alloyed powder, or shall we use separate powder, mixing the powder and then use it in the machine? So we had to characterize the powder and to study the flowability to ensure very good display of the powder on the plate. So we first try titanium and nickel separately. We mix the powder. Can you put the video? Oops, sorry. Yep. So on this small equipment that will mix, but it was very difficult to ensure the homogeneity, and as the transition temperature is given by the chemical composition, it was very difficult to control it. And then we calculate the flowability using this small wheel. And the result was that separate powder, as you can see on the green and blue curves, the flowability is lower than for pre-alloyed powder, and then our reference, which was titanium. But okay, we say, okay, the flowability is not as good as our reference, as titanium, but let's try it. And the result was not good at all. We had a lot of defects on the plate, and it was really catastrophic. So we decided to go for pre-alloyed powder. But the main drawback is that with pre-alloyed powder, we have very huge limitation in terms of temperature transformation. So we cannot do whatever we want. But okay, let's do this at the moment, and we'll see later on if we can improve the flowability of the separate powder. Okay, so the second step was to create samples and to perform tensile tests on the sample, and to find if we have exactly the same performance than nickel titanium from casting. So we make this small and very nice sample, and then we perform the tensile test, and this is the result that we had, which is quite good. I mean, it's encouraging because we can reach reversible strain up to 5%. And from casting, nickel titanium can have a reversible strain up to 8%. So, okay, it's not 8%, it's 5%, but it's good. It's good, and it's only the beginning of the work, and we know that there are many parameters that we can improve, so it's very encouraging. So we were, quite surprising, but very happy by this first result. And finally, we manufacture some first prototype of actuators. So we selected a rotative actuator. So here the idea is that this actuator shall give a rotation up to 90 degrees. And so we measure the stress during the transformation inside the prototype. And we also measure the torque given by the actuator during the rotation. So we can see that the torque at the beginning is almost 50 Newton meter, and then will decrease during the rotation, and will decrease quite significantly up to 13 Newton meters. These are some first results that are also not too bad, and especially to be able to give this 90 degrees rotation is very interesting with a torque which is it's not that high, but it's quite good. And once again, these are our first prototype, and we know that we can really improve several parameters. So we are quite confident to have better results in coming months. Okay. And so what's next? So now the project ended. So we reached the TRL4. So we already launched a new GSTP that we probably start in September. Once again with Thales, Alenia Space, and LEMS 3. So the idea is to continue working on this on this prototype to improve all the parameters, to work on the powder. And we would like also to try other powder, even if we know that it will be very complicated, but to try copper, aluminum, nickel, or to try other nickel, titanium X, hafnium, niobium, cobalt, and so on. It will be very interesting, but it won't be that easy. And another thing which is quite important is how to heat these components, because they react to temperature, so we need a heater to reach the triggering temperature. And so a new technology of heating shall be developed to be able to match the complex geometry or the complex kinematic of this 3D printed component. So this is also something that we will have to work on. And the goal is to optimize the performance of components, of course to reduce the volume and the mass, but more interesting is to have very complex kinematic and to have a behavioral gradient, meaning that you don't have the same behavior along the component. Okay. Thank you very much. If you have any question on the subject.